So this is the 2015 AP Physics 1 FRQ number 3. So in this particular problem we have our block. We're going to push it back to negative D, let go, block's going to move this way, release into some friction, the shaded part is friction, slow down and eventually stop at 3D. So the first thing they're asking us to do is to go ahead and sketch kinetic energy versus distance, and then secondly we're going to do potential energy of the block spring system versus distance. Okay, so let's do the kinetic energy first. So to do this, I don't know, I just like to make a little kind of data table here. So at the maximum negative D point, our kinetic energy is going to be 0. And when it reaches the 0 point, that's going to be kind of our max energy, whatever that is. And actually we know what that would be. That would be whatever our US max is. So our K max and our US max would be there. So 1, 2, 3, 4. I'm going to go ahead and just put it up here at 4, like this. We also know that at 3D, kinetic energy is going to stop. So that's going to also be 0, like so. Okay, and so the question then is, well, how do we connect these? So hopefully you notice that this is going to be some kind of, there's an x squared here in our US as we're converting. So question is, does it look like this, parabola up like this, parabola like this? You know, if you're not sure, just go ahead and find a point, right? So let's look at the halfway point. Let's look at D over 2. So we know at D over 2, we're going to have our US max, that's going to be at the maximum point, and then here we're going to have our US at D over 2 plus some kinetic energy. That's what we're going to look for. We're going to look for that kinetic energy, how much kinetic is right there. So this one, our max, we're going to have 1/2 K D squared should then equal 1/2 K D over 2 squared plus KE. So what you're going to notice here, let's just kind of pull this out a little bit. We have 1/2 K, and then we're going to have our D squared minus our D squared over 4 equals our KE, right? And so we're going to know, all right, our KE at that point, at our halfway point, is essentially going to be 3/4 times our 1/2 K D squared. 3/4 the value, right? So it's 1 minus 1/4. So anyways, essentially what that's telling us is that at this value, our kinetic energy is going to be 3/4. Remember, this is 1/2 D was our KD squared is our maximum value here. So this is going to tell us that we now have 3/4 of that value. So our point here is going to be right here. And at this point, hopefully you can see how you're going to connect that. We have our nice little parabolic shape. It's going to look like that. Okay, so how do we connect this to this? Well, notice at this point we just have our kinetic energy is essentially turning into work, right? So friction is doing work on the system or on the block and causing it to slow down, eventually stop. So the key to see how we connect that is we want to know, all right, what's the proportionality between kinetic energy and distance? Well, since kinetic energy is going to be turning into work here, we can say kinetic energy is proportional to force times distance, which you can see is a nice linear relationship. So to connect this, we're simply going to draw a straight line. And I don't have a ruler, but you guys should all have rulers when you're doing this. So anyways, this should look something like that. Okay, all right, let's do the potential energy of the block. So this should be much easier to do. So first of all, you're going to notice, so this is the kinetic energy curve, KE, oops, KE, and KE. So we know we have our maximum value is going to be right here. We also know that they should add up to the total. So this would be 0 down here. This was 3/4, right? 3/4 times the max. So this should now be 1/4 times the max. And so if we can see the way we're going to connect this, it's going to look something like that. And then at this point, the block's released itself, and so there's no more spring potential here. So our spring potential is just going to stay at 0. So this graph will just continue like that, and we'll have a 0. Okay, so this would be our US, US. All right, question number 2. Okay, spring is now compressed to twice, so we're going to push it back to 2D. They want to predict whether it will also go twice as far. Student reasons that since spring is compressed, it's going to increase in energy, and therefore it will slide at x equals 60. So which aspect of the reasoning is correct? So the aspect is that it's going to increase. So the student is correct in saying that the energy increases because, well, US equals 1/2 kx squared. So if D is doubled, and the spring US is quadrupled. Right, so x is squared, right? So if we double D, then we're going to square that out. That's going to be quadrupled. Which aspect is incorrect? The aspect that's incorrect is the fact that it's going to go to 6D. Okay, it will go farther, but it will not stop at 6D. So student is incorrect. In saying that it will stop at 6D. Because, well, as we saw before, energy was quadrupled. So the work to stop it is also quadrupled. And which means it should stop at 4 times farther. Okay, and I guess because I can write this out, work equals force times distance, force parallel to distance. Okay, so if work is 4 times, right, then distance would also be 4 times. Okay, it should stop at 12. All right, letter C, use quantitative reasoning. I don't know, in my opinion, I kind of already did use quantitative reasoning. I'm guessing that they want just kind of like a mathematical derivation of this. So let's go ahead and give that to them. Okay, so we'll just say, all right, we'll use our kind of our energy conservation, right? So we're starting with some potential, and that's going to eventually turn into work. So our spring potential, let's write this out as 1/2 k. So at the maximum value, that was d squared. Okay, and on our first case, I guess we could write this US1, W1. This should equal force times 3d. There's actually multiple ways you can go about this problem. Actually, I probably prefer doing it kind of more at the conceptual level like we did up here. But let's do it another way here. So let's see, how should we solve for this? Why don't we just solve for f? So f is equal to k over 6 times d. Okay, now let's go ahead and put it into our other equation. So for our second part, so US2 equals work 2. So we're going to go 1/2 k 2d squared this time, which equal force times, and then we'll just call this x. This is the value for x that we're looking for. Okay, so we're going to have 1/2 k. It's going to give us 4d squared equals f times x. Maybe I'll just make the substitution at this point. So we got k d over 6 times x. And then let's just go ahead and solve it. So what do? We can cancel out a d, cancel out a k, right? And that gives us, this will be 2 and multiply by 6, right? So we got 12d equals x. Okay, so I guess that's a nice little mathematical proof for distance. All right, last question says explain how they're expressed. So the reasoning in B, how it's expressed basically in our mathematical equation. All right, so I guess how would we write this? So D, so we did that right here, right? That's how we expressed it. So the student said energy doubles. Did you say double or just increase? Just increased. So I showed it with 1/2 US equals 1/2 k 2d squared. Right, so that means it was 4 times 1/2 kd squared. 4 times larger. And how did we prove that it was larger? So, I mean, I guess we just proved it. How do we say it? What do they want us to do? Refer to relationships you wrote in part C, not just the final answer you found by manipulating those relationships. So, so it's incorrect. Doubled, or I guess, yeah, the student said distance would be doubled. But if we have 4 times US equals work, should equal 4 times as well. I don't know, it's probably not doing a good job here. But since potential was quadrupled. And work is also quadrupled. Okay, something like that. I'd probably clean this up a little bit, but hopefully you get the idea. Okay, all right.